analysis is cluster analysis is very useful when you have multi-dimensional thing. In this case, I would assume that you are presenting 6 2-variable plot, but the k-mean clustering is done on 7 variable data. Am I right?
Yes, sir.
Okay, then that's okay. Okay, and yeah, to make it consistent, I would assume that the blue population on the top left is the blue population on the right. In which case, it might have something interesting, like the blue groups, right, buys not so much apple, but buys a lot of bananas or something like that. Because, you know, on the top left graph, the blue is sort of like lower down, and the top right. So if you're presenting this right, you should use blue for the same cluster throughout, right?
Yes.
Okay, good. That's good. That's good. So I just want to make sure. Okay,ครับ. And when you get to the gradient boosting, you actually have a mathematical manipulate that allows you. That one is just to run the model, right? So you already trained the gradient boosted tree, and this is sort of like a new person comes in, and then you put in. So this is a prediction, individual point prediction. Am I right?
Yeah.
Okay, good. Very good. Okay,ครับ. Excellent. Excellent. Okay, next.
Hello ค่ะ
Okay ครับ so you can go next.
Wait, just to make sure I have the right name, because we switch around. This the previous person was Kanokwan, correct? And before that was Panathon, and then before that Sorawit. Okay, so now I should be looking at Benyapat, right?
Yes, that is correct ครับ
Should I start now?
Okay.
Today I'll show you how I did my PISA price prediction project. This is what I'll cover today. So let's talk about why I chose to do this topic. I'm currently interested in making PISA and curious about the factors, features, or topics that affect PISA's price. And I think this is the core challenge for a PISA pricing manager to set and adjust the price to make the most profit. The main purpose of this project is to get interesting insight from the data, relationship between each features and prices, comparison between 5 companies, and the best prediction model to predict the price of PISA based on certain features. Let's take a look at my dataset. This dataset was downloaded online. By using the function dimension, it says that there are 130 rows and 9 columns in this dataset. First step is to clean the data. There's no missing value in this data. However, I made a few changes. The price in the dataset is in rupiah, so I convert to Thai baht, then drop the price rupiah column. Then I remove inch from the diameter column to get only numeric values. Let's move to data visualization. Here's the bar chart shows number of data from each company. Next, I use the list point plot 3D function to understand the shape and description of what data we are examining. So next 3 slides will be the box whisker chart to show the relationship of PISA and price from each company based on PISA topping, PISA variance, and PISA price. Here is PISA topping and price from each company. Next is PISA variance and price from each company. And finally, PISA size and price from each company. Move on to methodology and results. First, let's take a look at comparative analysis. The aim of comparative analysis is to gain better understanding of the features of PISA and its price. I wonder about the relationship between extra sauce, extra cheese, extra mushroom, whether it has an effect on price of each company. Therefore, I use the box whisker chart function to visualize and show outliers the data as shown in here. Based on the median of each box of each company, I assume that company A's pizza price has the most impact whether customers say yes or no to extra sauce. It's clearly visible that the average price in company A is above 75% one side for 3 out of 4 companies. If the customer chooses to have this sauce, company A would gain more earnings as company A charges more. For cheese and extra mushrooms, I assume that most of the company does not increase their pizza price. This might happen because people do not find cheese and mushroom to be appetizing. Next, I use let's plot to compare how much diameter affect pizza price from every company. It can be seen that pizza prices from company vary depending on the pizza's diameter. It shows that company A's and company D's diameters have the most impact on its price. As you can see below for company A and D, by increasing the price, the diameter grows rapidly. For other companies, I assume that pizza's diameter does not have much effect on pizza price. For this one, the goal is to create a prediction model that can predict the pizza price based on different features and find out what will happen to pizza price if we change the features. To make this test fair, I split the data into training set 80% and the test set 20%. The predictor is created using the predict function. The price in both will be predicted from the rest of the attributes. According to this dataset, linear regression happens to be the best method to perform. The predictor measurement examines the ability of the predictor that predict pizza price. Next, I created an application for pizza price prediction. Multiplet function allows users to change multiple variables. In this case, user can select the company they want. They can also change the pizza diameter, topping, variant size, and whether they want to add on extra sauce, cheese, and mushroom. To calculate how important each feature is to the linear regression predictor, I estimate sharp value feature importance for 100 pizza, using 5 samples for each estimation. This shows that the size of pizza is the most impact variable in predicting the prices. Next, I want to say if I change from linear regression to other available methods, whether they will still provide the same level of feature impacts or not. It can be summarized that pizza size is a key feature that affects pizza price. Here's the mind map. To conclude, this project uses data from 7 pizza features to predict the price in Thai baht and to have a better understanding of the relationship between pizza features and its price. The project includes the use of visualization and supervised machine learning. Thank you.
Okay, Kat. This is quite similar to the
Let me show you how.
Kanokwan's project. Okay, except with the additional feature was the feature importance. So that's something that's is quite interesting. Now you will notice if you go to the slides of feature importance that different models may actually choose different features. Okay, it's not always the case. It's not always, from my understanding, it's a little bit like this. If your model is largely linear, in other words, more factor this, there's not so much interaction between different attributes. It's just more additive sum, okay? If your models work in the similar way like this, then chances are it will pick up similar kind of features importance, okay? So you can imagine that, let's say, one class of model is very good on just taking the summation of individual predictive value. The sort of thing that I think your friend from doing the breast project was implying, that individual diagnosis adds to the likelihood of having cancer, malignant cancer. If it's that kind of additive, it has that kind of additive prediction, then it will pick similar features as important. But maybe another model would be more like a neural network where it takes interaction, it takes sort of like, x1 multiplied by x2 and so forth. Or you have something like more conditional break, like decision tree. If x1 is less than 5, goes one way, greater than 5 goes the other, and it goes x2, and that sort of thing. So you can imagine that maybe regression, gradient boosting and random forest might have similar kind of feature importance as opposed to feature importance picked up by neural network. Okay, but so it's not a given. It's not like if you fix a model like linear regression, then yes, you can say that if we talk about linear regression, the most important determinant of pizza price is size. The second most is topping or something like that. Okay. Now make sure, I think because it's category, if you were to do this individually, like say on a Python, be very careful that you one hot code the pizza topping. Okay, I think this one used Mathematica, so maybe automatically does that for you. But make sure if you were to use something like a Python, you have to do like one hot encoding or something. Okay,ครับ next.
Thank you
ครับ
ครับได้ยินปะครับ
ครับ Shotipat, right?
ครับผม
Yeah. By the way, from now on, just to say your name out loud a little bit, and then the name of your project. That way, make sure you're not confused. Okay,ครับ
Can you see the screen
Yes we can ครับ But I cannot hear your video clip.
Oh you cannot hear
Yes, I cannot.
Wait.
Maybe you have to share with computer sound.
Wait
Sorry, still cannot hear it.
wait you still cannot hear the sound
Yes, I still cannot hear it.
oh what wait let me try
this one because I'm using like my road and my topic is credit card default. So the data set I got here is from Campbell. So objective is I'll use the data set to compare if education, sex, marriage, and age, which one would lead to more credit card default. And it contains information on default payment, demographic factors, credit data, and etc. etc. This is from April 2005 to September 2005. Here's the comment. Okay, move on to this page here. So as you can see, this is gender, number 1 male, number 2 female, education. It keeps on getting lower when you school, university, high school, and then marriage, and then age. Yeah, there are numbers here. So when you see in the data set, there are numbers here, education, sex, all that thing. And then this is credit default. Number 1 means that you did not pay, and 0 means that you pay, so no default. Back to the slides. Okay, my map will start from statistical methods to probability models, foundation concepts, probability interpretation, classical statistics, and frequency. Again, as you can see here, I put the code here, so you can see. So what I did was the percentage over here. I just write the percentage of defaults. Yeah. So at first I drop the first element of data because it's a text. Well, this is a text, right? So I have to take it off. And after that, I just gotta separate number zeros and ones. And then I count them and then just plot it out. Yeah. So here, this is sex. This is marriage. I did the same thing. And age too. For age here, I just changed to Gen Z, millennials, Gen X, baby boomers. Yeah, because I have to sort the age out here. Like 9, 24, 25, 40, 41, 56, and all that thing. Yeah, I wrote the description over here. So yeah, I think I try to make it in details as much as possible. Yeah. And then yeah, plot it out as a bar chart. And then to conclusion, I think the one that affects the most is education because well, bank tends to lend more money to higher education people. As you can see here, the numbers here, it's kind of high. And lower education people has more credit card default. As you can see the percentage here, for number 5, it's like 90%. It's relatively high compared to graduate school, university, and high school. Yep. So that's it. Thank you.
Are you trying to build a prediction model with multiple factors?
This one, I can't really like. Can you hear me? Can you hear me?
Yeah.
Yeah. I don't think I can build like prediction model, but this one is just from like the data set, right? And then I make like clear visualization.
Yeah. I think this is a very good beginning. You have to do a visualization. Again, when you have a target variable, say that's your y, right? And you have the predictor variable, that's your x's, right?
Yeah.
You have to visualize your x that make sure that they're not all the same values. They have some distribution to it. They have some variation to it. And maybe you can do something like y as a function or as a correlation with individual x's, right? But you don't want to stop there. You don't want to just, you have 5 variables. You don't want to just have 5 plots that looks at x1 versus y, x2 versus y, x3 versus y, x4 versus y, x5 versus y, and that's the end of your project. You don't want to do that. Believe me, because in real life, first of all, you might end up with 200 variables, okay? So it's not going to make any sense for you to have a multiple or multivariate input, okay? A vector, a large multi-dimensions attributes, and then just look at them one by one, and that's the end of your analysis. I don't think that's what you wanted to, okay? This would be something that people did when they were doing linear regression, like logistic regression. Essentially, logistic regression just does this. It just looks at individual contribution of x1 and then x2 and x3, x4. So conceivably, you can plot x1 versus y, x2 versus y, x3 versus y, and just do it until you're done. But that's not the state of technology we are at. Okay, so this is more like a descriptive analysis of individual pair, y versus x1, y versus x2. But you have to do more. You definitely have to do more. Okay, Kap?
Okay, Kap.
Okay, who's next, Kap?
It's me ค่ะ
Go ahead, Kap. Go ahead.
แป๊บนะคะ Can you guys see this?
Okay, Kap.
Okay ค่ะ
For this project,
Can you guys
I
hear a sound?
would like to predict the house sales in King County, Washington, USA. The goals of this project is to predicting King County houses price and understand what factors are responsible for higher price. This project, the dataset taken from Gaggle website. This is an open source platform. This dataset involved 21 explanatory variables representing aspects of homes in King County, United States of America. For methodology, I want to do the exploratory data analysis to understand more clearly about this dataset. Within explore data, I will do the correlation analysis to see which variable is significant to each others and to see the positive trends and negative trends. In prediction part, I will do supervised learning as partition data, which is separate data into trend and test set. To clarify more on supervised learning is a method to train algorithms and predict the outcome accurately. In this project, I will use linear regression to identify the relationship between dependent variable and independent variables. Moreover, according to this mind map, regression analysis, which is our tools that we use, is in supervised learning. Here is the exploration of our dataset. I look at the relationship between price and other variables, outlier exists, and some variables have strong linear relationship with price. One interesting thing I noticed is that about latitude scatter plot. As you can see, the price skyrocketing when the latitude is around 47.5-ish. Then I go back to look at the GeoList plot and see that this area is around Bay Area and nearby Seattle, which just makes sense if the price is going to be higher based on the location closer to downtown. Here's the correlation result I got from all variables compared with each other. The matrix form is kind of very hard to demonstrate the value, so I use Vegas agency graph to demonstrate the correlation value that higher than 0.3. For prediction part, as I mentioned earlier, I separated data into trend and test set. I use predict command on trend dataset and then measure the predictor on test dataset. The model selected by Mathematica is a gradient boosted tree. According to the mind map, gradient boosted tree is a machine learning technique using in supervised learning within decision tree. And here's the result. As you can see, the gradient boosted model have very small number of root mean square and R square as well. So that is a good sign. And then I randomly selected house from dataset to see which variable impact on prediction the most. I use built-in function sharp value. In conclusion, latitude or location have the most impact on prediction, following with bedrooms, square feet above, so on and so forth. And this can prove the assumption about latitude earlier. Lastly, the interactive predictor, I let the user input their variables and then demonstrate them with the price prediction output. As you can see, you can put any number you wish. For example, bedroom with 3 bedroom or square feet with 1,000. And then the interactive predictor will calculate your prediction price.
Okay, Cup, very good. I like this. Especially with the idea of introducing the graph depiction of correlation. I'm assuming the color represents the strength of correlation or something like that. I wasn't quite clear. So just that's quite clever. There are many ways of representing graph nowadays. Graph visualization is a very big area, and so you can say something. You know, I would imagine that one of the most obvious way would be something like blue for positive value, red for negative value, or something like that. And the bigger the connection, the arrow, the thicker the arrow, the higher the value. So if it's the correlation is near 0, it's very thin. If it's near +1, it's very thick, or something like that. So there are various variation. What's fun about with Mathematica is if you go to this layer graph plot or this kind of graph plotting, they have different algorithm for actually organizing the points. You know, like maximum dispersion or hierarchical or circular, and different experiment with that, because sometimes you get a little bit more insight. You know, for example, if you have like a circle of friends and you want to know who's friends with whom, it makes more sense to do like a circular plot, right? Just line everybody in a circle and then who plot pairs with whom. You can have something that's sort of like separate out in maximum dispersion, or it's quite a lot of fun to play with. I like the idea that that you're mixing the latitude data with other thing as well. Now, presumably latitude data only works if you have some kind of, if you're restricted within, say, one city, right? Because in one city, yeah, you can say latitude data and longitude data. So you were not trying to make anything like the higher, the colder the temperature, the more expensive house price or something like that. So this is more like a zoning specific to the individual city. Okay. In the future, this link is something that can be improved, can be explored. Okay. For example, instead of having like a latitude, it would be something like a county name. Okay. You can imagine America is a very divisive society, and people from different counties, you know, just across the street from one another. You know, you can be literally neighbor, just cross one street, but you belong to a different school district. You pay different rate of tax. Your school is much better or much worse than your neighbor. So for America, a society which is very divisive, you can use that information like county breakdown or a tax district or represent electoral district. So there's a lot more to play with, but I think you've done the good architecture all around. Okay,ครับ. So this was what should we call this, prediction house price or something like that?
Yes ค่ะ
Okay, ครับ. Well done. Okay, ครับ Kanika, who's next?
นี่ครับผมแชร์สกรีนนะครับ
อาจารย์ครับผมมีเมสเซจอีกเมสเซจหนึ่งผมส่งไป
Oh, okay. I said Winian Feng. Okay, so we have Winian Feng next and Tehika Tesha Inchawang after. Okay, ครับ.
My name is Gantenakun, and the project I'm doing for the Big Data Analysis class is Top Spotify Songs 2010 to 2019. So let's go to a project overview. I'll be showing the introduction, data collection, methodology, the result, and the mind map. So one of my favorite things to do is listen to music. Recently, I have started to make music. Then I became curious. What variable comes into play with the popularity of a song? If there is a perfect song, what should this song be like in terms of variables? So the goals of this analysis is what type of music should be produced, what are the trends of the popular songs, and what is the perfect song consists of. Let's see the data set that I'm using. The data set I'm using is from a website called Kaggle. The name of the data set is Top Spotify Songs 2010 to 2019. This data set consists of 14 rows and 603 columns. The 14 rows will consist of song titles, song artists, genre of the song, song of the Billboard, tempo of the song or BPM, energy of the song, decibelity, loudness, liveness, valence, duration of the song, acousticness, speechness, and the popularity. And the columns will consist of list of the songs from 2010 to 2019. The dataset can be categorized into two types, nominal data and ratio data. The nominal data will consist of song title, song artist, genre of the track. And the ratio data will consist of songs year, tempo or BPM, energetic, everything that is a number. So the methodology. The first, I prepare the data. So I searched on Kaggle, Top Spotify Songs, and I came across this data. And next, I do data cleaning. So in the given data set, there were missing values. There are a row that have all values as zeros except the title, year, and genre. So I have to delete that row in the data file. And the song was sung by what's her name? Adele, yeah. And the analysis, I decided to use the data visualization as it has given the answer that I wanted. I didn't need to do any supervised or unsupervised learning in order to get the solution that I wanted. So I just go with the data visualization. So first, I had to find the most popular genre in order to find what song I have to make. And we can see that dance pop was the most dominated genre in the industry for the last decade. And next, I visualized all the other variables, such as the BPM of the song, the BPM trend over the years, energy trend over the years, the live singing trend over the years, acoustic values of the song over the years, and duration. and I graphed it. So we can see the result. So the result is that if we were to make a perfect song, I would suggest to make a pop genre, specifically the dance pop. It has dominated the industry for the last decades and is still the most popular genre today. And the song has to keep it under 4 minutes, as the trend is shifting towards slightly shorter songs, and the loudness should be between -5.5 to -5.7 decibel, and the acoustic is a key area where it should focus their efforts on. So the conclusion comes to that there are many variables come into play into making a perfect song, and the data is not having the song from 2020 or 2021, so it can be slightly different now today. And this is my mind map. Thank you.
Okay, I think you started with a very interesting, very exciting premise, the ability to literally extract what makes a perfect song. Having said that, I think you sold yourself short a little bit. Again, it may be the case that you can guess, you can look at individual, again, this is sort of like the same comment that I was talking about. What was your friend, the other friend who was doing like credit card or something? Yeah. So basically, you just analyze Y versus X1, Y versus X2, Y versus X3, Y versus X4, okay? This does not convince me. I'll tell you why it does not convince me, okay? The reason it doesn't convince me is because the best X1 and the best X2, if they happen to come together, you have to show that. Okay, I think implicitly you were trying to say that because of the way the music industry works or whatever, if you highlight individual factors, X1, X2, X3, X4, X5, you get the best of each, and then you get the perfect song. That may be the case, but you haven't proven it here. Okay, in other words, if you say the best is under 4 minutes, okay, the best is under 4 minutes, and the best is dance track. Well, you haven't even shown to me that that majority of song can be dance track and under 4 minutes. You see, if that were the case, you have to show as well that such combination exists. Okay, so again, if you say under 4 minutes is good, dance track is good. Okay, you have two questions to answer. A, can you have dance song and dance track under 4 minutes? Okay. Number two, in your data. If it's not in your data, and let's say you build advanced neural network model that makes a prediction, and that prediction say the best, you get a lot of popularity if you have a dance song over 4 minutes. Okay, or under 4 minutes, sorry, under 4 minutes and dance song. Okay, you're still not sure if that is an extrapolation. Remember that that graph I was showing you with Mathematica, the combination, right, with the discussion on the Shep value. Now, if you have this value and that value in this combination, it may not exist in your data point, right? So if the model say the best thing is to have dance track under 4 minutes, first of all, you have to check if it's in your data. Okay, and if it's not in data, how valid are you? It's extrapolation. It's not. So machine learning or any kind of analysis we're doing with data is extremely precise and extremely powerful for interpolation. Extrapolation is a little bit iffy. It's a little bit dangerous. Okay, so you haven't convinced me there. Okay, but the concept of looking at this this analytics of song and so forth is very good. Having said that, let me give you another warning. Remember, I gave a warning to your friends who was doing the abortion problem, right? You have to look at the shifting demographics so your baseline changes. Well, same thing with music industry. There's a trend, not in terms of the listening audience, but the producer. they tend to be doing the same thing. You know, they use the same voice dynamic compression. You know, in the 70s, they didn't use dynamic compression. Now they use a lot of dynamic compression. So you can say, well, you might find that the most popular song use dynamic compression a lot. Well, that's just a fact of life that everybody does that nowadays. You see what I mean? The baseline has changed. The baseline has changed. Okay, the music industry, by the way, has got more generic. You know, you use auto-tune and all that, and so it's more. In the future, you don't need a real artist. You just need a computer algorithm. And I think what you're doing is sort of like pointing to that direction. But again, it's the shifting. It's your data does not really represent human psychology with respect to music. It also reflects simultaneously the music industry. Okay, so if all the best, if the best producer happen to use a lot of dynamic compression or loudness, or you know, then that's what you'll find. Okay, so take into account the underlying baseline a little bit. Okay, again, that example I was just giving you is a silly example. Can you have a dance track under 4 minutes? Now, when I was your age, you know, life is different now. When I was your age, we go to clubs. We go at, you know, 11 o'clock in the morning, at 9, come back 5 in the morning. That was in London. And each dance track lasts 8 minutes. Okay. So the idea of dance track that lasts 4 minutes would have been silly to me when I was your age. Okay. It's like, well, what kind of, it's a pop song, have 2 minutes. There's no such thing as a dance track under 4 minutes. You know, so that's just an example. Okay, so but maybe this is the case now because you know, I don't go to clubs anymore, obviously, at my age. So maybe dance tracks are now 3 minutes long, but when I was your age, it was 8 minutes. Okay, very good. Next.
Thank you, Kap.
Welcome.
I'm William from today.
อาจารย์ครับมีรายชื่อเพิ่มขึ้นไปอีก
One more. Okay.
ในไลน์กรุ๊ปครับไม่ใช่ในไลน์กรุ๊ปในไลน์อาจารย์ครับ
Okay. Gotcha. 3 more. Wow. Okay, ครับ So Winian, you're up.
Welcome, I'm William from today. I'm going to introduce you my big data project, a new way to detect your body fat level. And this is my project notebook. So if you want to take a closer look at my code, my data set, you can scan the QR code right here. And my presentation will be separated into 5 parts: motivation, about data set, solution, process, and my conclusion. So firstly, motivations. So we all know that body fat level can be a really interesting fact to know and can be used for different purposes in different fields. However, measurement of body fat level can be a complicated and challenging task because most of the measurements are really inaccurate, and the accurate ones use the density measurements, which can be a really costly methods. So I wonder, is there an easy way to measure body fat level without density but with high accuracy? So my solution is using a data set to make a predictive model to determine one's body fat percentage without the density. So I got a data set from Kaggle. It's a listing of percentage of body fat with various body circumference measurement for 252 men. And my data content have in total of 15 factors. And this is the sample data. You can see there are in total of 15 factors. And then before getting into details, let's start by showing my mind map. So on the right-hand side, for the data analysis part, my data format is numerical type and in terms of ratio scale. And for analysis, I'm going to use a system model to make a prediction model because I know the X, which is a variable, different variable in the data set, to find out Y, which is the body fat level. Let me shift it. So yeah, so in the end, I will be using a regression analysis to make this final prediction model. And for data visualization, I'm going to use a scatter plot and a heat map for visualizations. On the left-hand side, for machine learning, I'm going to use a XGBoost to support my prediction model. And for static methods, I'm going to use 4 regressions to make a prediction model. And I'm also going to use a moment for my graphing and my visualizations. And let's go back to my slides. So here, this is the overall methodology for what I'm doing next. So firstly, I will import the data observations, clean data set, and the full regression, XGBoost, evaluating, comparing the models, and conclude my final linear models. So firstly, I import the data sets and from Kaggle, and there's 252 observations and 15 attributes. And then I make a data observations. Firstly, I use a heat map. So the red highlights represent stronger positive correlation relationship, and the blue highlights represent stronger negative correlate relationship, and the right represents 0 relationship. So I put them into an histogram to have a better visualizations. So in terms of importance, so we can see that in terms of the importance, we can see density is the highest, but we're not gonna use it. So we're gonna use not the density, another top 5 for our regressions, and then we put it into a scatter plot. So using a scatter plot supports my finding of high correlation among the 5 variables, and additionally, I know the graph is normal. And before we start, I will remove all the norm values and the density variable, which I don't want to see in the data set. And then I will start doing the 4 regressions. So firstly, I'm going to do the linear regressions. So we can see the output of the R-square of the model is really high. And the other detail I will conclude later together with other regression. And secondly, I use a principal component regression to see the output if after we reduce our dimension of the data set. And then I did another 2 regression in terms of graph, the rigid regressions and the lasso regressions. We can see in the graph, the uptick lambda for both graph looks the same, but for lasso regression, the graph of log is quite different because the curve is no longer smooth on the top. But before we conclude the regression, I also use an XGBoost library to implement the gradient boosting decision tree algorithm. So I can use this approach to support my regression prediction model to be more accurate. So lastly, I compare all my 4 regressions. I can see firstly from the root mean square distribution, the RMSE. The linear and lasso regression have around the same, and is also the highest, while the rigid test and the other 2 has the lowest RMSE. So this makes the rigid regression perform much poorly than the other 2. And for the R-square score, we can see that lasso and linear test also perform the best, and also explain about the same amount of variance at 70%, while the other 2 data set perform at under 35%, which is much lower. So by using lasso and linear regressions and my results from the regression methods, I can make a final prediction, which is a linear model of body fat, which you can see on the slide right now. And also, personally, I predict my own body fat level using this model, and it's really accurate. It's around 90% accuracy. So, but however, I think this still limitations and improvement for this project. So because this data only consider 252 observations, so the result could be biased. And also this data set only contain men's data. So it's not a really good prediction model for women. So I would like to continue this project in the future by using a mixture of both gender with a larger observation to make the prediction model even more accurate. And that's all for my presentation. Thank you for watching.
Okay, very good. I think you made a very good effort at using the regression-based method to do your analysis. What I like is this. By looking at the correlation plot, maybe you should have your slide up a little bit. Can you slide up? Share your slide again.
For the
go to maybe correlation plots between your factors a little bit after, I think. Yeah, you should have the, yeah. So something like this would be very good indication that using a linear regression may run into problem because you have multi-collinearity. And based on this, you are then motivated to use like lasso regression or ridge regression. So that's good. I like, so emphasize that reasoning. I think one of your friends used both linear regression and lasso regression without giving the motivation. I think it's better to give a motivation of why you're using lasso or ridge regression, and mentioning that you find that your explanatory variable are multi-collinear is certainly a very good reason for that. And this is borne out in the correlation plots. Okay, I'll go to the result table a little bit. Yeah. So let me see. I had to look down. It's a little bit small. Lasso train, lasso test, R square. So actually, it's kind of strange, isn't it, that you actually get a better fit on a testing than a training, right?
Yep.
Okay, so I'm not sure why that would be the case. So this looks a little bit interesting. Okay, it doesn't have to be wrong. It doesn't have to be wrong. But normally you go the other way around, right? You get a very good fit on an in-sample or a training, but when you go to a testing data, it gets worse. This case, it seems to be that, R square improves in test. Root mean square error also gets better with test. Can you make sure that you actually label this right? It looks a little bit funny. It looks counterintuitive. Okay, that's all. Okay.
I think I will go check it again later.
It is possible. It is possible. It's not like it hasn't happened before. You build a model and you get this accuracy, and you go test it to the data it hasn't seen. It gets even better fit. That is possible, but it's not normally the case. So this is a little bit funny looking. Okay. Good. Okay, Cap. I think we have. There are people who wants to present this week because they have to take vaccine or whatever. So that takes, next person is Tejika, right? So let's have Tejika, Teya, Rajanan, and Pimnipa, and that's it. That's the end of today. Okay. So we have 4 more. Okay, Tejika, you're up.
Can you see my screen?
Okay. Yes, we can see your screen.
Happiness can change and does change according to the quality of the society in which people live, says John F. Hilleville. The findings show that happiness and well-being are important indicators of the world's economic and social development. The objective of this report is to find the relationship based on 6 factors, to know why each factor influences both high and low happiness score countries, and to predict the healthy life expectancy at birth based on the happiness score of all the countries combined. The World Happiness Report focuses on the 6 factors, including economic production, social support, life expectancy, freedom, absence of corruption, and generosity. The size of this dataset is 1,926 rows and 11 columns. The table shown on the slide extracts only the data of Thailand as an example. The World Happiness data is from the Gallup World Poll, who conduct studies and record all the most important issues worldwide. In this report, I will mainly predict and analyze the countries based on the happiness score using line plot application, bar chart, list plot, community graph plot, geographic region value plot, and predictor application. I will explore the data and find relationships between countries and each factor of the happiness score to identify the inferences why some countries rank higher than others. Moreover, I will compare the country with low happiness rank with high happiness rank in order to see the difference and tackle the problem. At the end, I will predict the healthy life expectancy that is interactive, which will be highly accurate and useful according to the data from 2008 to 2019. Moving on to the data visualization. First, bar chart. I randomly selected 10 countries out of 150 to see any abnormal increase or decrease in numbers in each factor throughout 2008 to 2019, but some countries have up to 2020. From what I can see, there are no abnormal changes except for generosity and perception of corruption factors. I will do more research on why there is a big change in those numbers and will note it into the report. Second, I created an interactive line plot application and chose to do 2 examples, happiest and least happiest countries. For this, you can choose the countries and choose to show only one attribute or all attributes. This is a quick comparison between the 2 countries. Third is the line plot. I used line plot to visualize the correlation between the attribute using average attributes for each country. For example, the second graph shows if life ladder is high, healthy life expectancy will also be high. Fourth, Pearson's correlation coefficient. I use this to calculate the correlation matrix to create a community graph plot. A weighted adjacency is to visualize the considerably correlated attributes with the coefficient greater than 0.4. It shows which factors are related to which factor. What I can see from this is the health life expectancy has strong correlation with life ladder, log GDP, and social support. The fifth one is the geographic region value plot. The number is the average attributes for each country in each factor, and this can make it easier to see and understand. Now, the most interesting one, prediction. Before I did the interactive predictor application, I combined all the countries in each factor to see the variables that have more impact on the prediction, which is log GDP. These are the prediction based on the number I chose for each factor randomly. This is the mind map. The report will help people understand more about what makes people happy, which will be beneficial for the near future. Thank you. Does anyone have any questions?
Okay, Cup, very good. This reminds me of your other friend's project as well. I think energy usage or something. Just make sure that you are not confounding the input variable with the predicted variable, right? So if your output is an index of happiness and your regressor or your axis also contains some of the statistics used to define the index, then you're actually predicting itself. Okay, so just make sure that you don't have that problem. I didn't catch the detailed definition of your X's and your Y. Just make sure that that's not the case. If it's the case, then you can just say it's a visualization. It's not a prediction. Okay. Again, it's just that and that applies to everybody, right? A lot of time, Y is something that is a phenomenon like cancer. Okay. In which case, it's something you really know. You want to predict with something you knew. Okay. But if it's about social metrics like happiness or sustainability or clean energy, a lot of time the Y is an index created from a bunch of statistics. And so you have to make sure that those statistics are not themselves used as predictor, in which case, it's confounded, right? Okay, just make sure that that's not the case. Okay, just make sure that that's just so what you have to do is for each of the target that has to do with this metrics of happiness or metrics of energy or sustainability, make sure that you look at the component. Okay, again, the simplest thing would be to say like, the happiness is partly indexed by GDP. And if you put GDP as predictor, well, you're predicting yourself. So just make sure that that's not the case. But other than that, it's very good. Okay, Kap?
youค่ะ
We are down to Taya, right? Taya, you're up.
Hello ค่ะ Carbon dioxide is being released constantly, whether it's a man-made or natural. It's almost impossible to stop it completely. However, it is possible to reduce the amount being released. So many scientists are seeking for the best solutions. Carbon emission data set allows us to view the efficiency of the current solutions, as well as the effect on people's habit and the world's trend from different time periods. This machine learning project, the aim is to discover the trend of carbon dioxide emission based on different demographics, to see the difference in carbon dioxide emission from the previous year compared to the year, and to find the best model for prediction for carbon emission in the following 10 years. This data set consists of 59 columns and 205 rows. Figure 1 displays the amount of carbon dioxide emission in metric tons per capita in relation to the time period by each country and continent. This data visualization is implemented using Manipulate to allow a specific country or continent to be selected by a drop-down menu. This graph visualizes how different time period impact the amount of carbon dioxide emission. In this example, Syria is able to reduce the amount of carbon dioxide emission from 2010 to 2018. Figure 2 displays the difference in the amount of carbon dioxide emitted from the year and its previous year by the selected country and continent, as well as the consecutive years being represented. This graph shows how different time period or different trends could impact the amount of carbon dioxide emission, while also seeing the trend of each country's and continent's carbon dioxide trends. In this case, we can see a huge drop in a yearly different amount of carbon dioxide in the year of 1890 to 1990. This tells us that there is probably less climate change movement and high economic stability between the 2 years in Europe and Central Asia. Moving on to comparative analysis. Figure 3 displays as a list plot. This shows the amount of carbon dioxide emissions being released each year in the United States, China, and Thailand. While the x-axis represents the consecutive year, y-axis represents the number of carbon dioxide emission in metric tons per capita. This plot is best used to represent the trend. In this case, we can see that the United States emitted the most carbon dioxide, followed by China and Thailand. However, the amount of carbon dioxide being emitted in the United States has been declining since around 1977, which is different from Thailand and China, whose carbon dioxide emissions are consistently increasing over the time period. Figure 4 displays the difference between the amount of carbon dioxide emission from the year compared with the previous year. In this case, the figure shows the difference of the carbon dioxide emission from 1960 to 1961 to the difference of carbon dioxide emission from 2017 to 2018. This graph is displayed using animated. This would allow us to compare the climate change movement trend to the economic stability for each country from the difference in the amount of carbon dioxide emission. Factors associated with the method utilization include the increase in the amount of information that can be conveyed and statistic display. This figure can be concluded that United States has the consistently highest amount of yearly difference of the carbon dioxide emission, followed by South Korea. These countries had consistently shifting trends and undergone serious economic adjustments. Figure 5 displays a list plot, prediction of carbon dioxide emission in Thailand in the next 10 years using time series model fit. The fitted model will be used to simulate the time series for the next 10 years, 15 times
These simulated data will be used to forecast the average trends for the next 10 years. Figure 6 displays the prediction of carbon dioxide emission by the selected country and continent for the following 10 years period in list plot. Utilizing time series model fit to find the fitted model by random function, which ran 15 times to find the best fitted average for the model. In other words, to apply the above function to create application to forecast the carbon dioxide emission data for each country. In conclusion, this project aims to visualize and analyze the amount of carbon dioxide emission from 1960 to 2018, with names of the countries in the world to see the trend, to see the yearly difference in the amount of carbon dioxide emission, and to discover the best model prediction. Here is the mind map for this machine learning project.
Okay, Kap, go back to the mind map a little bit. Okay, can you share? Okay, I just want to see where the time series prediction model is highlighted. By the way, what is the time series prediction technique that used? You didn't mention the methodology.
So it's like a method built mathematical built-in function that is created for like time series data set.
Okay, so make sure you go in detail a little bit. With time series, you have to specify perhaps, not only what variable you use, but also like maybe window size and whatnot, how far you look back and that sort of thing. So that'll be some elements. But I think it's very interesting. So it's a mixture of visualization as well as depicting trends, maybe per capita improvement in CO2 emission in some country versus in Thailand and so forth. So I think it's very good. Okay, but just be a little bit more clear. None of you, I guess, with the exception of one paper, one presentation, actually cites any kind of reference in terms of methodology. Just make sure that in your project write-up, you don't omit that. Okay, just make sure, be very precise about what methodology you use. In theory, somebody should be able to read that paper and replicate it, right? Now, the transparency with which you describe your data source, that's already pretty good. Like you say, it's from Keiko, it's from this page, it's from that, or maybe even you generate it yourself, that's fine. But if you generate yourself, you keep it on GitHub and you share it so people can replicate. But in terms of methodology, it's a little bit unclear if somebody wants to replicate your results. Okay, so be very sure. Okay, Kap, Rajanan.
Let me share my screen.
Hello, everyone. My name is Rajanan Gambhir, and this is my big data analytics term project presentation. Here's the outline, which consists of 6 main topics, as you can see here. Let's get into it. So firstly, allow me to introduce my data set. My data set is star type classification, which originated from NASA. The source of my data set is Kaggle, as seen with the link below. So this data set contains a total of 7 columns or factors with 241 rows for entries, including headers. It's an open database with a size of 8.42 kilobytes. Looking at each column, we have temperature, relative luminosity, relative gradient, absolute magnitude, color of spectrum, spectral class, and star type from 0 to 5. Moving on, let's talk about the primary objective of this project. There are two key components to achieve. First is data visualization, specifically interactive. Focusing on the dynamic visualization, I utilized the manipulate function and deployed it to the cloud server for easy access. The second objective is unsupervised machine learning, essentially clustering analysis. So there appears to be a relationship among the factors, which is actually quite interesting. Now, allow me to exit the PowerPoint and open Xline for a more comprehensive view of the mind map reference. All right. So first, let's take a look at the right subbranches. When we talk about data analysis, my project revolves around the interactive visualization part of the engine, which is the analysis informs the model using approach and explains findings from the analysis. Now, under the data analysis pipeline, my project focuses on mainly the scatter plot data visualizations, which falls under the visualizing relation. Now, looking at the nodes on the left, as you can see here, machine learning is also relevant to my project. In particular, clustering analysis, which falls under the unsupervised paradigm of machine learning. I've actually done both hierarchical clustering, such as agglomerative, and also non-hierarchical clustering, essentially the elbow method of the gaming clustering algorithm. Back to the slide. I've actually snapped a couple of demonstrational graphics, which I would like to display. So first, here is the manipulate function graphic visualization demonstration, where you can see that I've utilized three factors, where the start height is the basis with an x-axis of relative luminosity and y-axis of relative radius. And the link to the cloud deploy is on the top left. This is another manipulate demo where I use different factors like colors of spectrum as the basis with temperature as the x-axis and absolute magnitude as the y-axis. And secondly, this is a clustering analysis graphic demonstration in which I have chosen to cluster the combination of temperature and absolute magnitude factors because the result is actually quite interesting. On the left, you can see the list plot with an automatic method which clusters nearby values, but the tab below specifies different types of hierarchical clustering. Now, this is a non-hierarchical clustering, Gaussian clustering algorithm using the elbow method, which gives an optimum number of 15 A clusters. Now let's take a look at the observations and analysis. The key findings are as shown here, and note that K equals 6 is the elbow point where the inertia starts to decrease in a linear fashion, as previously shown in the demo. Based on the observations, I've actually analyzed that highly luminous stars tend to have negative absolute magnitude and high temperature. And for the gaming clustering, neighbor points to the inflection point are also considered to be almost as efficient, which is why K equals 6 to K equals 9 are the best selections. In conclusion, even though this data set is not extremely large, there is still potential as previously seen with what I've done to try to make it look interesting. Lastly, I would like to end by mentioning that I will most likely continue to attempt pursuing projects like these even after the course terminates for the fun of it, perhaps even devise a prediction machine learning model in the near future. All right, that's mostly everything for me today. Thank you all very much for listening. Have a great day. Bye-bye.
Okay,ครับ. First of all, I think you need to get a new microphone or something. I had the same problem. Okay.
Soaring prices, massive shortages. What's next?
Your microphone, I really can't hear very well. It's got a lot of buzz like when you speak. Okay. So you might want to re-record the presentation. Now, I think it's very interesting what you were trying to do. And I think I remember I made the comments in the workshop session as well. Okay. Having said that, let me say again, you know that in terms of star classification, there is a well-defined physics of star classification. So what you might want to do is to say, well, how about we present an alternative or unsupervised way of classification? Okay, that would be an interesting project. Okay, but what you would certainly have to do is acknowledge first that there already is a physics-based or physicist star classification. If you go to internet, I guess, look up the keyword main sequence or main sequence star or Hertzsprung-Russell diagram or something like that. Just look up main sequence star. There are actually existing scheme of classification. So what you might want to do is to say, compare existing scheme with unsupervised machine learning or something like that, you know, with your k-means. So that'd be interesting as well. But certainly it's not a substitute. And as I mentioned in the workshop session, and I repeat my message again, data science steps in when you don't have a better mechanical, scientific, technical, chemical, physical, economic theory. If you have all that, that's a better explanation. You would go with that. Data science or data analytics comes in when you don't have those. Okay, so if you have a main star sequence classification, it would not make that much sense to go ahead and jump in and with unsupervised learning. But it's a good fun. I think it's a very good learning experience for you. And so I would write the paper as, say, alternatively, you know, like being curious, what would the star sequence classification look like if you instead of using the scheme the physicists use, you use the scheme by unsupervised learning criteria. That'd be an interesting way of presenting this project. Okay, right. But it sounds like a good fun. Very good. Okay, so now we to the last person, Pim Nipa, and the rest of you would start at 1 o'clock next week. Okay, Pim Nipa, you're up.
Can you hear me right?
Go ahead, Ja.
Morning, my dear Professor Pumchai. I'm proudly presenting to you my project topic regarding heart failure analysis using unsupervised learning, k-mean clustering, the elbow method, as well as visualization. Cardiovascular disease are the #1 cause of death globally, taking an estimated around 18 million lives each year, which accounted for 31% of all deaths worldwide. People with cardiovascular disease or who are at high cardiovascular risk need an early detection and management, wherein a machine learning model can be a great help. The main purpose of this project is to perform machine learning to achieve the interesting insight from the data set, association between patient health attribute information and heart disease, the k-mean clustering analysis to identify patient group, and best analysis model for k-mean clustering. Let's move on to the data set, which contains 918 rows with 12 columns. I got it from Kaggle, where the data set was created by combining different data sets that are already available independently but not combined before. Firstly, I start by importing data and distinguish feature from target column, which is heart disease, as well as nominal scale feature that need to be converted to numerical value to process machine learning later. As for the data cleaning, I have removed false data and left with 746 rows, then converting nominal feature, which is label information, into numerical value. As for my method, I've used k-mean clustering to group the data as well as the elbow method to determine the number of clusters in the data set. Based on the slide, I might say that I have arbitrarily picked two numbers, which is k equal to 3 and k equal to 5. I would like to share a little insight that firstly, I didn't notice the false data, so I haven't removed it yet, and my elbow is significantly seen on the k3 and k5. But luckily, after I have removed my data, there is no significantly new value of elbow shown in the graph. So just want to share that please explore your data before performing tasks, because if you are not lucky like me, you might have to reprocess again. Here is the result grouped by K3, which the data were grouped into 3 persona, or you can call it centroid, with heart disease percentage. Based on the result, we will be focusing on group 1, which has 88% affected by heart disease. We can easily notice that the patient in group 1 have a higher value of O peak, asthmatic chest pain type, exercise-induced angina, and flat ST slope, as well as having a lower value of max heart rate compared to other groups. Here is the histogram visualization of the distributed data grouped by K3. It can be obviously seen that the value of max heart rate for group 1, the blue graph, which are 88% affected by heart disease, is lower than other groups. As for the O peak, group 1 has distributed value of O peak in a higher range ranging from 0 to 4, while the majority of other group has a value equal to 1. The majority of group 1 has exercise-induced angina, while other group have not. As for the ST slope, the majority of group 1 has a flat slope, while other group have non-flat slope. Lastly, the majority of group 1, which is affected by heart disease, has an asymptomatic chest pain type, while other group have not. Let's move on to our other K, which is K equal to 5. The data were grouped into 5 groups, where I will consider group 1 and group 2 to be a safe group that has only 10% and 7% affected by heart disease, while group 0, group 3, and group 4 are considered to be a risk group. As for the histogram visualization, we can see similar pattern as K3 that the risk group will have lower max heart rate, O peak distributed in higher value range, and has exercise-induced angina. Here is some interesting insight that group 4 is a spatial group, which is a risk group that has non-exercise-induced angina, same as the safe group. As for the ST slope, it will be the same pattern as defined in K3, that the risk group will have a flat ST slope and asymptomatic chest pain type, while the safe group has not. Here is the mind map to visualize the associated element within my project. Hope my presentation can guide you guys how to detect and prevent a heart disease that may happen to anybody. Just hope it's not any one of you. We all know that some risk factors for heart disease cannot be controlled, such as age, family legacy. However, I have pursued my goal to take a step forward to determine the risk and lower the risk by encouraging changing in some controllable factor, for example, lifestyle, exercise routine, and eating diet in saturated fat, trans fat, and cholesterol. Thank you.
Okay, Kap, this is very interesting. Having said that, I'm confused on one point. Why is this an unsupervised learning exercise? It seems that you have both the explanatory variable as well as the target variable, right? Now, let's say, okay, let's imagine that you have something like this. This is your situation. You have all your X's and you don't have the Y, okay? You don't have the Y. You do the unsupervised clustering, and then you separate into 3 groups. And then based on those 3 groups, you go and measure the value of Y, okay? Then you can notice that maybe group 1 and group 2 and group 3, which is naturally clustered, have different Y values, okay? Maybe group 2 has higher Y than group 1 and 2 and so forth. You can do that. But this does not seem to make sense yet, because in this case, in your case, because you actually have the percentage of heart failure. Literally, you do that. You do have that, okay? So it makes little sense to say, well, let's do a cluster analysis, unsupervised learning of the X values and ignore the Y, and then go check out what the Y value is, because you already had the Y value to begin with, right? You see what I mean? You see what I mean? I mean, it could be a different situation where you would do this thing. You do unsupervised first because you don't have the target, right? And then you go measure, something like that. But in this case, you've done the groundwork. I would imagine that you can revise the problem formulation. It sounds to me that there's no reason to make this an unsupervised learning. After all, you really want to care about predicting the heart failure, right? Okay.
Yeah,
okay, but very good. But you done all the preparation. But definitely, I wouldn't say throw away everything, but I would imagine that this is good for supervised learning exercise.
Yeah, but my point is like I want to find more type of like positive case. Like for example, like the group, I can remember the group, like the group 4 that is purple graph. It's a spatial group that has heart disease, but yeah, that is.
Yeah. But the group, when you do the unsupervised learning, you don't have the target variable in there, right? Right. Yeah. Just you have other factors in there. Okay. Yeah, it just turns out that by making, okay, let's imagine this. Let's say that you do the unsupervised learning on the x's, and they have similar value of y. Then what's your next step, right? You can't do much, right? Because literally you just say people look differently, but that has no impact on your prediction. Now it happens that once you've done this clustering, one group has higher heart failure. Yeah, then you can say, oh, this kind of people, okay? But it seems not straightforward. Yeah, straightforward exercise will be, well, if you want to predict heart failure. It's a supervised learning problem, okay? Now you can then do this, by the way. You can then, well, do cluster analysis on the x's to see that for people who also have high value of heart failure, are there different groups? So maybe there's a people who are eating a lot of fat and not exercising, they have heart failure. But there's also another group that is very different, but also has a high value of heart failure, like works hard or whatever, okay? Or congenital disease or something like that. Yeah, I'm not saying that don't do unsupervised learning in a supervised learning problem. I'm saying you have a supervised learning problem, okay? So go with that first, okay? But other than that, very good. Okay, so it seems like you guys are doing very well. Some of you have some misunderstanding. I think this is actually helping me, by the way. Next class, meaning like next year, what I'm going to do is I'm gonna take out some of the machine learning aspect, because I will package that in a machine learning class, and I will spend maybe 1 or 2 more classes on the nature of data itself. Because I think you have different area of interest, and data, they don't have the same status. For example, one is a malignant versus benign cancer. That's a phenomenon in itself. The other one is a proxy for something else, like index for clean energy. Okay, so the nature of data, how much truth there is in the data itself, I think is something that, to be honest, I think I did not spend enough time on it. Okay, I did not spend enough time on it. Hopefully, if you have a good solid math, if the next next class have more solid mathematical background, I will forget about that revision class and spend it more on the data description, on the nature of data, how data arises, what kind of value can you extract, what kind of interesting case can you think of data analytics. So hopefully next class I probably try to make the adjustment. Okay, but very good. Okay, Kap. So Kiran, again, you're more than welcome to resubmit the video and the presentation. I'm going to send you a presentation on the write-up format in the next couple of days. I would also encourage some of you who did a very good, very interesting interactive application to think about publishing on paper with code, in which case you would have to use a LaTeX format. So I'll send you the overleaf link for that, okay? Not today and probably not tomorrow, I'm a bit tied up, but I'll do that in the next couple of days. Okay, I'll see you guys next Tuesday, okay? So I'm going to send you another template, a blank template of just the people you have today. So please put in that file instead, because it's ordered. Okay, so everybody will have the same thing. I'll send it to you in a few minutes. Okay,ครับ. I'll see you guys next Tuesday. Okay. Well done, all of you. Okay,ครับ.
Take care ครับ
Thank you